Okay, so we're going to go ahead and start, but if you're still working on the quiz, continue to work on the quiz. I know there are a lot of long problems. This is not a short quiz by any stretch of the imagination. But if you finished, we start today on page 16. And if you're taking the quiz and you miss any of what we're about to do, it'll be on YouTube in an hour and a half, so you can check it out later. But go ahead and take your time finishing our quiz. So one quick announcement, I still have the sign-up sheet for the resume cover letter interviewing workshop. It's here on the desk. I'm going to submit that later today. If you decide you're interested in one of these after today, just contact me and I can give you the name and email address of the person that you're going to register with. It's down here at the bottom. All right, and then one other announcement. So today, and I say this without looking at anybody in particular, today is the last day to withdraw from any of your classes here at GCC with a grade of W. So if you are thinking about withdrawing from some class, this one, another one, have a conversation with your teacher, have a conversation with your academic advisor, but have these conversations soon. End of the business day today is the last day to withdraw. Next week is kind of funny. Monday is Veterans Day. There are no day classes, but if you have a Monday night class, you can go to it as usual. Wednesday next week is a funny day. We follow a Monday schedule during the day. It doesn't affect us. And you follow a Wednesday schedule for the evening classes. So we're going to see each other next on Wednesday, but technically it is a Monday day schedule. Any questions on the calendar? Okay, and just while it's here, right around the corner, we've got the Thursday and Friday of Thanksgiving week coming up soon enough. Okay, so we are right now finishing quiz number 6. Also assigned as of right now is, yes, Bubba. The Thursday is Thanksgiving, and the very next day is also a day off. So let's see. So we're finishing the quiz. Project 6 is now officially assigned. I've put them on the table, so make sure you grab a Project 6. And today we cover something called optimization problems, and that's where we are there. Our next quiz is not coming up for a while. It's on the 19th, 10 days from now. Maybe that's Monday of the Thanksgiving week. Okay, so, you might want to make a note that Project 6 is due on November 19. So that project is due November 19. So on page 16, so we're going to skip around a little bit here because the quiz took longer than I wrote down on the quiz with the 22-minute time. So let's skip around and see if we can answer some questions about that picture, which maybe looks a little familiar to you. What I'd like us to do is identify the x-coordinates of all the global extrema, but I'm going to give you an interval here. Well, actually, before I give you an interval, what's the highest point anywhere on that graph? What letter? J. So J is the highest point of all the dots that are marked. But assume the graph goes forever left and right. What's the highest point now? Yeah, there isn't one, right? It goes up to infinity. And is there a global minimum somewhere? No. If it goes down forever, no. So at the moment, there are no global extrema. No highest point anywhere, no lowest point anywhere. But let me modify the question. Same graph, but how about right now, let's just look between A and J. So starting at A, the first dot, ending at J, the last dot. Where is the highest point anywhere in that interval? It's at J. Where's the lowest point anywhere on this interval? Is it D? So we'll just make a note that the global max is at J and the global min is at D. Everybody buy that? What if I change the interval again and I ask you to look only between C and E? Might be a little bit hard to read, but this guy right here is the E. So we're looking for the global max and the global min on that little interval in there. I'll highlight it in red from C to E. Where's the highest point anywhere in there? Is it C? And the lowest point? Is it D? So max is at C, min is at D. So do we buy that okay, a function in general doesn't have to have an absolute highest point. Like if this one went forever, it doesn't have an absolute maximum. But as soon as I restrict you to some closed interval, do you buy that there's going to be a maximum somewhere? Okay, so it turns out there are little restrictions on the theorem, but basically this is true. If you look at a function on a closed interval, it will have an absolute max, a highest point, and it will have an absolute min. Okay, so here are the funny kind of restrictions. Suppose that I gave you a graph like this. So it goes up to there, it's got a hole right there at the top, and it goes down to there, and we'll close it, and we'll close it. A, B, C. There's the absolute minimum, A. Where's the absolute maximum? So I heard there isn't one, I heard there's two of them. So what do we think? Absolute highest point. Well, so I'm telling you that up there at the vertex of this parabola is an empty circle. I'm calling it B. So what are the two of them? So if you folks are saying two, just like on either side, just kind of like, right. And so it feels like there should be, you know, like some last point in there that's the highest one, but there is no last point there. And Joe, I think, was kind of getting at that when he said it's not definable. You can pick any number that you want. Let's say that B happens to be the number 2. And you can say, oh, okay, then if I just go to 2.000001, then I'm going to be right up there. And I'll say, sure. But there's a point higher than the one that you just named. If I said 2 point and then gave you a few more zeros and then a 1 at the end, my point's going to be a tiny bit higher than yours. And so it's kind of counterintuitive and it's difficult for some folks to accept, but there is no highest point in this graph. No matter how many zeros you stick on after the 2, I can always add another 0 to your number. And if you tried to say, okay, let's go 1.99999, let's say 4 nines, well, there's a higher number. There's a higher point from that one by adding a 5th 9. And if you decide you're going to be real clever about it and say, okay, but I'm going to go forever, well, it turns out that 1.999 forever is the number 2. And so there's no way around kind of saying, I'm going to add enough zeros so that we can get that last point. There is no last point, none at all. Yeah, it's a good question. We can talk about that right after class. So take my word for it right now. Okay, so what failed? I said that if we just look at a function on a closed interval, we should have a highest and we should have a lowest. What was wrong with this function? It's not continuous. That's the problem. The theorem that we're about to see is going to say, oh, if it's a continuous function on a closed interval, then you'll have an absolute max and you'll have an absolute min. But if you don't have continuity, funny things can happen. I'll give you one that's even worse about this picture here. So suppose that we have our graph and it's going to look, how do I want this to look? I want it to go, start here, go up there, and then we're going to have it jump down to there and go up to there. A, B, C. Okay, on the closed interval, starting at the far left, A, and ending at the far right, C, where is the absolute max? Yeah, there's no max and there's no min for this one because the maximum, unfortunately, just happened to blink out of existence right before we got there. And the minimum, unfortunately, happened to not blink into existence until we just missed it. So a function that's, you know, it's not terrible, still does not have an absolute max or an absolute min on this little interval. So the theorem that we're hopefully kind of starting to believe is this thing called the extreme value theorem, so named because we're looking at the extremes, the absolute high and absolute low. If a function is continuous on a closed interval, then the function has both an absolute max and an absolute min on that interval. Okay? That's our theorem. So let's go back up and again think about the interval between C and E. That was this highlighted in red interval. Where was the absolute max? Is it C? Where's the absolute min? D. Okay, so C is special because it's the highest point here. Just on this piece from there to there is what we're looking at. And the highest point is at C and the lowest point is at D. But C and D are special for two different reasons. D is special, I would say, just from the graph. What's special about D? We have a name for points like D. It's kind of like a vertex. It is a local min. That's close to the vocabulary word we're looking for. It's a turning point. And yesterday, or last class, we defined it to be a critical point. On the quiz, it said find the critical points, right? Places where the derivative is 0. So I would say D is special on its own accord. D is just special for this function. It is a critical point because it's flat there. Would you say that C is special? If I just gave you this picture and I didn't highlight the red interval, is C special? C just seems to be a normal random old point that the graph happens to hit. C isn't really special because of the function. What made C special in this problem is the domain, is because I said look between C and E. So by being a starting point, C became special. The graph doesn't really do anything funny at C. The graph does something funny at D, right? It really changes its behavior at D. C is just an ordinary old point on the graph. But C becomes special. It's kind of artificial because I said, hey, look, starting at C, and look all the way out to E. So let's see if we can answer this question down here, number 6. To find the absolute extrema on a closed interval, we're looking for 2 kinds of points. You've got the critical points. Those are, I would say, special in general for the function. But you've also got the endpoints, the artificial points, the ones that I make special just because I put the domain on those endpoints. And so it turns out to find the absolute max and absolute min, all we're going to do is evaluate the function at each critical point and at each endpoint, and we're going to grab the highest and lowest numbers we see. So coming back up here again in this picture, if I asked you to evaluate the function, I didn't give you the rule, but evaluate the function at C, what number do we get? We get 0, right, because we're on the x-axis. It's hard to see the numbers, but is that maybe around -2? I can't really tell. I think it's a -4 down there, but it's... Oh, that's a -1 at the bottom? Oh, that's a -2 that's written. So maybe that's a -1. Okay, and then maybe this one, -2.5 or something. Is that fair? So just looking at those 3 y values, even if we didn't have the picture, but if we had those 3 y values, which one is the absolute max? 0. That's the biggest number in this list of numbers. Which one is the absolute min? It's -2.5. So if we just have a list of those numbers, it's easy. So first goal for today is to be able to not use a graph, and find the absolute extrema of a complicated function on an interval 1, 5 in this example. So here's what we're going to do. The goal is to make a table, x, f of x, and there are exactly 2 kinds of points that go in this table. What kinds of points? So we've got endpoints. Those ones are easy because they're given. What are they in this problem? 1 and 5. 1 and 5. And the other kind of points that we want to stick in here are the critical points. These are the ones that require work because we have to find them. So again, I'll stress the format of this question because this is a fairly standard calculus question. Find the absolute extrema of some function on a closed interval. That's our giveaway that we're doing this kind of funny process. I'll repeat that at the end of this process, but that's what we're looking for to know we're supposed to make this table. Okay, so let's see if we can find the critical points. This is a calculus task. What do we do to the function? Take its derivative, f prime of x equals (6x squared minus 30x plus 36). And critical points come from 2 sources. Where did critical points come from? Derivative is undefined or derivative is 0. This is never undefined, so we immediately skip to the equals 0 part. And let's make our lives a little bit easier by doing some algebra first. What number comes out of all those? 6. That is a good thing to factor out. And again, even though hardly any quadratic is factorable, most of the ones you see in math class are factorable. It's just a big coincidence. I've been experiencing it for years. I don't know how it happens, but minus, so what do we get here? Is that 3 and 2? Yes. So what are the critical points? 3 and 2. Okay, we're about to take those two numbers and put them somewhere. Where do we put them? Into that table. We're going to throw them into the function. So we'll put them in our table, 3 and 2 in any order. And I will highlight them in yellow. And I'm going to point out, we're not doing a sign test here. The question doesn't say find the local maxes and local mins, like the first derivative test on your quiz today. This is an absolute extrema question. So we're not doing a sign test. We're just plugging each of these things into the original function. So maybe split up the work at your table and just shout out some numbers when you get them. Anyone? 23 is good. 55. 28 and 27. Anybody confirm any of those numbers? Or get something different from any of those numbers? Just looking for somebody else to weigh in before we make our conclusions. Okay. So this is easy, right? Especially if you have a calculator, but even without, it's arithmetic, right? All we're doing is plugging numbers into a function. So that part's easy. And now it's our job to come to our conclusions. We're looking for the absolute max and the absolute min. Did I get these backwards? So it should be 27 for this guy and 28 for this guy. Thank you. Okay, so the absolute max, we'll move this up just a little bit. Absolute max is the highest y value that you see. What is it? It's 55. So that happened to be at an end point. So I'll say 5 comma 55 is the absolute max, the highest point anywhere in this interval. And the lowest point is at 23. 1 comma 23 is the absolute min. That's right. Yeah, all numbers in the table are just going back into ordinary F. Okay, and just for kicks, I'll do this real quick. I'm going to graph the original function. Trying to get this out of your way. So it's 2x cubed minus 15x squared plus 36x. Okay, and now let's think about the window. And I claim that, all right, so let's just look at a standard window, zoom 6. Perfect. So I know it's breathtaking, isn't it? So I think I said on the first day, and maybe it didn't have any meaning at that point, but I said that, you know, like the technology is going to be better at graphing things than we are. No matter how much practice you have, the calculator is going to be better at graphing things, but the calculator is stupid and it doesn't know where it should go. So this is where we have to use the calculus to tell the technology where to look. And so with the work that we've done in the calculus, we can get a really nice picture here. So first of all, the x's that are important were given in this problem. What's the domain of this problem? 1 and 5. So let's go between 1 and 5 on the x's. And now the y's, this is the part of the problem where, like in a college algebra class, you just had to guess and check and try negative 100 to 100 and fiddle around. But now we can get a very tight window on this interval. What's the smallest y that you're going to find anywhere on this graph in that window? Is it 23? What's the, whoopsies, what's the biggest y you will find anywhere on that window? is 55. And so if we graph this thing, we're going to see it starting at the bottom left, ending at the top right. There's a little dip in there. You can see how subtle that is. And if we weren't looking at a nice picture, we might completely miss that there is a little tiny hitch in this graph. The dip is only one. There's only a one difference between the low point and the high point in this dip. That right there is at 27. That right there is at 28. If we didn't know to look right here, probably wouldn't even see it. It would probably look like it just increased continuously the whole time. Any questions on that? Okay, go to the next page. We're going to skip this problem in the interest of time, but I will remind you that on the first day we talked about what parts of a lake freeze first. And we said, okay, the cold water in the lake is in the bottom of the lake because your feet are cold when you're swimming in the lake, but the lake freezes from the top first. And it turns out there was some density thing happening here. And so here was this crazy formula for the volume of, was it 1 kilogram of water? So it turns out the volume of water depends on its temperature. This was the formula to tell you what the volume is at a given temperature. And then it was really difficult to graph this function. Like I gave you guys a minute or two on the graphing calculator to just play around and try to find a good window, and it is hard. And the reason it's hard is because that graph is even more subtle in terms of its turning around than this one. And so I gave you some, I think I gave you like some random quadratic equation to solve. I just made one up. I said, solve this quadratic equation and use whatever solution you get to the quadratic equation as the point to put in here. And I don't remember what the number was. It was something like 3.9, something like that. And then it turned out that was the bottom point in this graph. The graph bottomed out at 3.9, but it was a real subtle bottoming out. It didn't go way, way down. It was just down a tiny bit. So the quadratic equation that I got, do you guys have any guesses? If I wanted to find the absolute min of this function, what calculus thing would you do? You take a derivative and set it equal to 0. So if you go back and look at the very first problem we did on, in packet 1, you will find this crazy looking quadratic equation that at the moment, at the time, it came out of nowhere. But now you know where did it come from? It was the derivative. That crazy quadratic I gave you is just the derivative of this thing. And so, so maybe have a look at this, over the weekend or something, and just go back and refresh your memory about how we did this problem. There was mystery around this problem on day 1, but the mystery has been, I don't know what the right word is. The curtain's been open. I mean, there's no mystery anymore. It's just take a derivative and set it equal to 0. Okay, let's go down to, what should we do here? Let's have somebody read number 9 here at the bottom. Nikki, can you read 9 for us? Okay, so we're going to do some problems that are slightly different from this one. I just want to repeat one last time. If I ask you to find an absolute extrema of some function on a closed interval, that is the big tip-off that we are doing this thing where you just make a table with the critical points and the endpoints, okay? So it's a giveaway once you've had enough practice recognizing it as a giveaway. Continuous function on a closed interval, we're making a table. So these problems, a little bit different. We're finding the absolute extrema just like before. So it feels like maybe we're doing the table. But what's the difficulty with this thing? It's not a closed interval, right? It's closed on the right, but it's an open interval on the left. And so it could be one of those kind of functions where, it's like maybe it goes like this and it ends over there, and over here we'll put it up there. But then it's an open circle, and so maybe there won't be an absolute max because we just don't quite get there. So in a problem like this where there's an open interval or a half open interval, we'll need to do some extra analysis near the 0 just to figure out if we can really think about what's going on. For this function, well, we don't have, it's just all real numbers. So we'll analyze the critical points, but we're also going to have to figure out what's going on at the far left and at the far right. Does it go up forever? Does it go down forever? Does it go to some horizontal asymptote? It's just a little bit more work, that's all. It's not as clean a process as the other one. So let's start here with part A. Okay, so it's Calc 1. What's our favorite thing to do? So take a derivative. And then it now feels like our favorite thing to do with the derivative is set it equal to 0. So let's set it equal to 0. What can we factor out? Or x squared, yeah. Critical points, 0 and 3. Are these critical points in the interval? Because the interval is all I'm caring about. 0 is not in there. But there's going to be some, like this will really require some analysis on our part, because 0 is important in that it's an endpoint. It's also important in that it's a critical point, but finally it's not there. So I'll put like quotes around the 0. I mean, it's going to be in our analysis, but it can't be a final answer for us. So yeah, it is a repeated thing, but so what are you saying? Do you think it just like kind of goes through 0, or? But if it bounces on the 0, then doesn't that make it like a min or max? I think you're on the right track. You've got something happening here, but you have to distinguish between whether you're thinking about the graph of the derivative or the graph of the original function. Right. So it is a bounce on the derivative. I buy that. So then we need to make some conclusion about the original guy. So I think you've got good. So on the original, I think if it bounced on the derivative, I think it's going to hit x equals 0 and maybe think about turning around, but then not. Yeah. Okay. So what do we do here? We can't just take stuff and throw it into a table. So we're just going to do essentially the first derivative test. You guys put an f prime over there. Put 0. Put 3. And we're looking for pluses and minuses in each of those intervals. Once we have our numbers, where are we plugging them in? Yeah, are we plugging them into f or f prime? F prime. That's where these numbers came from. Okay, to the right of 3, what number do you want to pick? 100. Oh, great. So let's pick 100. Do you want to go the first one or the second one? Second one. Go to the factored one when we're doing our sign test. So plug in x equals 100 right there. What kind of a number do you get, including the square? Positive. Plug in x equals 100. What kind of number is that? Positive. So out here, definitely positive. All right, and then on the in between 0 and 3, maybe 1. What do you get for the product of these things when x is 1? That's a negative. And technically, for our purposes, to the left of 0 is meaningless because we stopped our question here at 0, but I still feel like there's information that we want out there. So plug in a number that's less than 0. And what kind of a thing do we get? That one's also negative. Remember, the x squared is going to be positive no matter what. So what is the original function doing to the far left? If the derivative is negative, then f is doing what? Is decreasing. And then it's flat. And then what is it doing? Decreasing again. And I think, Garrett, this is what you were seeing with that bounce in the derivative.
Yeah, there is.
Right. And then bigger than 3, increasing. So I can really start to get a feel for the way that the graph looks. I know that we are decreasing until we get to 0 when we're flat, but then we just decide to continue to decrease some more until we get to 3 when we're flat, and then we increase forever. So that's at 0, that's at 3. So We're only interested in looking between 0 and 3.5. So I'm going to put an open parenthesis here to say starting at 0, but don't include that point. 3.5 is out here someplace. I'll put like a bracket out there. I'm quite confident talking about one of the things, the max or the min. Which one are you confident you know about right now? The max or the min? The min. It's clear the minimum is where? It's 3, without plugging any numbers in. You can just understand, because on the entire interval here, it's decreasing until 3 and then increasing. And that's the only thing that's happening in this interval. So 3 is definitely the absolute min. Don't even need to know what the y value is. The absolute max, though, there's actually a couple of possibilities, and we still need to analyze further. The absolute max could be at one of two spots. Where could it be? It could be at 0, or it could be at 3.5. And so really we need to know, if we were to stop the graph at 3.5, if you're stopping the graph here, then where is the absolute max? Is it 0? But if 3.5 happens to be a little bit further out, now where's the absolute max? Is it 3.5? So do we understand we got to figure out like where it ends really? So I feel like we're looking for two y values that we need to compare. Where do we want to find the y values? At the original equation, and what x's are we interested in comparing? Is the 0 and the 3.5. Those are the things that I'm visually trying to understand which one is higher. So I'm interested in knowing f of 0, and I'm also interested in f of 3.5. Okay, so f of 0 is 0. What about 3.5? Negative 21.4. Anybody else confirm that? Okay. So where's the absolute highest point? Is it 0 or is it 3.5? It's at 0, just comparing this number to this number. Okay. 0 is higher than negative 21.4. So the highest point on this graph must be at 0. So what's the absolute max on this interval? There isn't one. That's right. If it was at 3.5, then the winner would be 3.5, because 3.5 is a candidate. The correct answer is it should be at 0, but 0 is artificially excluded here, so there just isn't one. So how can we write this? I guess I'll say max would be at x equals 0, but x equals 0 is excluded. So there's no max. The min was at x equals 3. We established that a while back. Josiah. So Josiah is right, and so let's even put a plus sign there to say we're going from the right towards 0. And so this is a common attempt to try to resolve this idea of, well, okay, so it should be at 0, but we don't quite get there, but let's get as close as we can. And it appears that limits do exactly that, because this limit says you don't get to plug 0 in, but you get as close as possible. But we just can't get there. And so it's for a lot of folks, it's kind of hard to swallow that there's just no last point. But this is a characteristic of the real numbers. You give me that open interval, there's no way to identify what's the first number in this list of numbers. There isn't one. So it's a valiant effort, but like the final conclusion here is that there's just no maximum in that interval. So what to take away from this one? I cannot give you a process for how to solve these problems. I gave you the process on the closed interval. What are the two sources for things to throw in the table? Critical points and endpoints. Those are the ones that we throw on the table. It's always that process when it's a closed interval. But if it's a partially open interval or if it's on an all real numbers, I don't have a process for you. You need to take a derivative, find the interesting points. Those are the critical points. Doing a sign chart gives you a real good sense of the behavior. Are we going up? Are we going down? And then you just have to think. You got to sit there and analyze and think about the possibilities. So I don't have like a step-by-step process I can give you. It's really just a matter of immerse yourself in the behavior of this function and then try to come to some logical conclusion. All right, so I think we have time for one last one. We'll do number 11 here. Is there a funny typing thing in this one? Yeah, there's another British pound. So that's just a less than or equal to. So that's right in here. It's just less than or equal to. For part B. Oh yeah. Yeah, you can fix this too. That's a g of x. Okay, so let's go to Chris. Chris, can you read number 11? Mm-hmm. Okay, so there's a lot of abstraction happening in this problem. So let's be clear. A is a constant. It is the normal or resting radius of your windpipe. I don't know exactly where my windpipe is. I'm assuming it's somewhere in here, but I don't know exactly what part it is. But maybe the radius is ½ inch or something like that. Okay, so it's roughly cylindrical, and so it's got a radius at rest of ½ inch. But the radius changes. I'm assuming the radius changes as I talk. I assume the radius changes as I breathe. And so the rest radius is just if I'm just sitting and just kind of chill, but it is some number, so that's a constant. But then the radius changes, and so we've got different radii, and I'm hoping that this thing here kind of now makes sense. What's the smallest the radius could be of my windpipe as it's opening and closing? It could be 0 if it were completely closed. What's the biggest it could be? Well, it's my resting radius, whatever that is. I can't get bigger than the normal radius of my windpipe. So it's somewhere between 0 and A. And the idea here is that for all these different radii, the velocity at which the air comes out is a function of how big this space is. All right, and so there's the function right there. It's some positive constant k. I don't know what k depends on, but it's just some constant times a minus r times r squared. And what we're interested in knowing is, well, what's the fastest that you can get air to come out of your mouth? What radius is going to happen? Like if you just take a big deep breath and blow as hard as you can, there's going to be some natural radius that your windpipe heads towards. And the question is, what is it? Is it your resting radius? Is it half of your resting radius? Is it always, I don't know, 2/3 of an inch? I can't imagine it's going to be the same for everybody, but this is the question, okay? So let's see if we can get started on this one, and maybe you guys can finish it. I'll say that the level of abstraction that's happening here is going to turn some folks off, and I will just say try to push through. It will build your math muscles if you just push through, even though there's k's and a's and r's. R is the variable. R is like x. So what's our favorite calculus thing to do? Make a derivative. B prime of r equals. So what rule do we have to use? R's are x's. That's a product rule. All right, I don't feel like doing that. So what can I do instead? First, distribute, right? It's not terrible to distribute that. So we're distributing from both the left and the right. So I got KAR squared minus KR cubed. All right, I think that's easier to take a derivative of. So take a derivative. R is the variable, so K's and A's are just constants and they're just hanging out. So for KAR squared, the K is hanging out, the A is hanging out. What's the derivative of R squared? 2R. That's my derivative. K hangs out, A hangs out, 2R. Minus, which letter is hanging out in this one? K is a constant multiple, it stays. The derivative of R cubed, 3R squared. So I know we're over, so let's conclude and you can finish later. What's our favorite thing to do with derivatives? Set it equal to 0. Ultimately, you're going to have a table here with R's and V of R's. And I can tell you right now, 0 and A go into the table because those are your endpoints. And then whatever you get from this equation also goes into the table. So just in case you decide to try this later, I will give away the answer so you know whether or not you got it. I think it's 2/3 the radius of the, yeah. So it turns out that the maximum is 2/3 of whatever your resting radius is. So shoot for that as you try this one. What's that? And as you try to cough, just think about what fraction of resting radius you're at. Yeah, good. All right, have a great weekend. Sorry for going over.